And now we're going to finish up our parallel treatment between polynomials and integers and divisibility by talking about GCD and linear combinations. In particular, we're going to look at expressing the greatest common divisor of two polynomials as a linear combination of the two polynomials. So we're going to review Bezout's identity for the greatest common divisor of integers. We're going to state what the corresponding theorem is for polynomials. Won't be too bad, just everywhere you see an integer, replace it with a polynomial. And then we'll give an outline of what the proof looks like. It's going to look very similar as it was for integers. All right, so here is Bezout's identity in case you've forgotten, but I'm pretty sure you haven't because you've used it a couple times pretty recently. Let a and b be integers, where at least one of them is non-zero. Then there exists integers x and y such that the greatest common divisor of a and b is equal to ax plus by. And again, you're maybe not too surprised, but we have a very similar result for polynomials. Let f be a field and let f of x and g of x be polynomials, where at least one of those is non-zero. Then there exists polynomials k of x and m of x such that the GCD of f of x and g of x is equal to k of x f of x plus m of x g of x. So here's kind of an outline of the proof, what it's going to look like. We're first going to define our set of linear combinations. So we're going to define S to be the set of all polynomials a of x, such that a of x is equal to k of x f of x plus m of x g of x for some polynomials k of x m of x. And just like in the old days, we're going to exclude the zero polynomial. Now we're doing that for actually two reasons here. Before we did it because it's easy to get zero in there by just letting k of x and m of x both be zero. But here it's also important because the one bad thing about having the zero polynomial is it doesn't have a degree. And as we'll see, the degree of those polynomials is going to be very important to us. And well, we'll see it very soon, right now. The degrees of the polynomials are all non-negative integers, so we can use the well-ordering principle on them. So we're going to find a polynomial that has the least degree, the minimum degree, among all polynomials in S. We're going to prove, you have to prove that one of those is going to be monic, and then prove that if r of x is a common divisor of f of x and g of x, then r of x divides d of x. And first of all, the importance of that is that r of x can have a degree no bigger than d of x. And to prove that, you'll use the fact that d of x is a linear combination of f of x and g of x, and then play around with that equation to get a contradiction. All right, so here's what the outline of the proof is going to look like. We got to prove that d of x divides f of x. We got to prove that d of x divides g of x. It's going to look very similar as it did for integers. We're going to start with f of x, and we're going to use the division algorithm to get f of x equals q of x d of x plus r of x. We want to prove that d of x divides f of x. That means we want to prove that r of x, that remainder, is equal to 0. Now, we may not know it's equal to 0, but we know that the degree, if it isn't equal to 0, then the degree is less than the degree of d of x. So if r of x equals 0, then we're happy. So we're going to assume that r of x is not equal to 0 and solve that equation for r of x. So then we're going to plug in d of x equals k of x times f of x plus m of x g of x into the same equation. So the equation I'm talking about is the one that says f of x equals q of x d of x plus r of x. We're going to plug that in for d of x. And that will enable us to write r of x as a linear combination of f of x and g of x. So I'll let you do the algebra on that. It's not too bad, but it's important because that's our first step into proving that r of x is actually in S, or is a possible candidate for being in S. Now we know that r of x is not equal to 0. That's our assumption. That means that r of x is going to be in S. And that's a contradiction because r of x has degree that's smaller than d of x, but it's in S, and we define d of x to be the polynomial in S with minimum degree. So that gives us a contradiction. Then we can repeat that exact same argument for g of x, and that tells us that d of x divides evenly into both f of x and g of x. And that tells us that d of x is the GCD of f of x and g of x. All right, so now I have a few problems for you to work on for in class. The name of the file is Polynomial GCD and Linear Combinations, and you'll find it right below this video.